What we did last time is we used the tree method to try and unroll our recurrence relation for the Fibonacci runtime. So we kind of got to here. What I want to do is continue with this, and let's see if we can solve this. So just as a reminder, these branches really represent pluses. Right? At the end of the day, we want to add all of these nodes in our tree to arrive at our runtime. And so just looking over here, it's not immediately clear how we're going to get some sort of pattern. Right? But if we were to go one more level down and apply our recurrence relation again, right? If we were to erase this and to apply the recurrence relation, we're going to get O of 1. We're going to get all O of 1s. And then we're just going to apply. Let me just write this O of 1, these O of 1s first. We're going to get O of 1s, and then we're going to apply our T's. We're going to apply our T's below. I'm not going to write them out, but they're going to look something like that. There's going to be, each of these nodes is going to have two branches or two children of its own. Right? And this is going to continue on for some amount of time. And at the end, we're going to hit our base case, right? And in all of these cases, we're going to keep subtracting either 1 or subtract 2. But in either case, if we start with n and keep subtracting 1 or keep subtracting 2 or some combination of both, n is eventually going to hit this base case. In other words, at some point down our tree, we're going to get all O of 1s. Right? At some point at the bottom of our tree, we're going to get all O of 1s. And this right here, when it stops, is what we have to figure out now. Just like we did with the factorial, we want to figure out the height of this tree. So one thing you might notice is that the way I drew this might be a little misleading, is that the heights of this tree, the height is different at different places in the tree. In other words, our rule was that if we look at our recurrence relation, we would put that this O of 1, or this O of 1 over here, we would put that O of 1 as the root node, and then we would put these two recursive calls as its children. In particular, the n-1 child will go on the left, and the n-2 child will go on the right of the O of 1. So if we continue that pattern, the left branch is always going to be n-1. Likewise, if you take the right branch, if you keep taking the right branch, it's always going to be n-2. Right? But in both cases, we said at some point we're going to hit n equals 1 or n equals 2. So now the question is when. So we're going to analyze the height of this tree, but only at the extremes. In other words, only in the rightmost part of the tree, and only in the leftmost part of the tree, and only in the rightmost part of the tree. So I'm going to redraw this in a minute. Let's look at the rightmost extreme part of the tree first. I'm going to use a different color. Just right over the recurrence relation. What is this height? Well, our rule was for taking the rightmost branch, it's always going to be by doing t of n-2, right? We're always going to be subtracting 2 from our n all the way until we get down to n equals 1 or n equals 2. And so ignoring some plus or minus 1 issues, which are not that important in our asymptotic analysis. ignoring those plus minus 1 issues, if we keep subtracting 2 every time, if we start from n and we keep subtracting 2 until we hit 1 or 2, well then this is going to take about n over 2 subtractions, right? If we start from n and we subtract 2, n minus 2 times, then we're going to get 1 or 2, right? We're going to hit our base case in n over 2 operations. And let's look at this leftmost extreme over here. Right? This leftmost extreme corresponds with us always taking n minus 1. And so what is this height? At some point we're going to get O of 1, right? So what you might notice is that if we subtract 1 each time, well then it's going to take longer for us to hit this base case than if we subtracted 2 each time, right? In the rightmost case, in the rightmost extreme, we're subtracting more each time until we get to 1 or 2. Here we're subtracting less each time until we get to 1 or 2. So this is going to result in about n operations. Again, ignoring plus or minus 1 issues. This is going to be about n iterations, which corresponds with a height of n. And so I'm going to draw this extreme O of 1 below that O of 1. It's going to end up somewhere here. And so the height of our tree in the leftmost extreme is going to be about n. So our tree in full is going to be a somewhat lopsided tree. It's going to end up looking like that, right? And so what we noticed in this video, just to recap, was that this tree ends at different places, right? The heights of these the heights of this tree are different in the left extreme and in the right extreme, and that came from the fact that this recursive call is kind of lopsided, where we have an n minus 1 but also an n minus 2.